Hello class, in today's lesson we're going to be looking at factorizing by completing the square. The learning intention is to know the expanded form of a perfect square, to be able to carry out the process of completing the square, to know how to factorize by first completing the square, and to understand that not all quadratic expressions can be factorized and to be able to identify those that can't. Now, I'm sure that you're probably sick of seeing this particular diagram over here, but again, I just want to reinforce that we've already covered many different ways for you to actually factorize, and the reason why we factorize quadratic expressions is because this allows us to easily calculate what our x-intercepts are by also using our understanding of the null factor law, okay? Now, the only two particular methods that I want to kind of address to today is the product sum method as well as completing the square, okay? So these two particular methods over here, they are predominantly used to factorize quadratic equations when they're in a trinomial, so meaning that's got three terms in the actual expression. And what we're going to be doing is we're going to quickly go over the pros and cons of each of these methods. Now, please do recall that these particular factorizing methods, you can use one or the other, but it's really important that you guys understand which one's better under certain circumstances. So let's quickly review what are the strengths and disadvantages of each of these different methods. Now, for the product sum method, this is a very popular method that we've been predominantly using. So the pros of this is that it's the most easiest and it's the most popular method to use when we're trying to factorize quadratic trinomials. The disadvantage is that this particular method won't always work for all trinomials, okay? It will probably factorize maybe 70% of all the problems you'll encounter. So that's the disadvantage over here. On the other hand, completing the square is another factorizing method, and this will factorize most quadratic equations. Probably can factorize maybe up to 95%, okay, of the problems that you may encounter. However, the only downside of this is that this particular method over here is quite time consuming. There are a lot of steps involved, and many students often find it a bit difficult to use this particular method over here. So what I'm going to do now is I'm going to show you what are the limitations of the product sum method so you can understand and have a better appreciation of the completing the square method. So in this case over here, we already know that the product sum method involves finding the factors of a, c, and then finding the sum that gives you the middle term b. So in this case over here, I've technically always taught you that for a monic equation, it's always the factors, find factors of 6 that gives you the middle term 7. Technically, it should be the factors of a and c, but because in a monic, a is equal to 1, I don't really get you to consider that at all. So in this case over here, a and c gives you 6. What are two numbers multiplied together that gives you 6 but adds up to 7? In this case over here, that'll be positive 1 and 6. So we know that this can be easily factorized using the product sum method, okay? And in my second example over here, if I was to do a non-monic, or I'll do the same thing, I'll find out the product of a and c. In this case, that's 24. Find out what two numbers multiplied together that gives you 24 add up to 14. In this case, that would be positive 12 and positive 2. And therefore, you use the regrouping method. And I haven't showed you full working out, but once you've done this successfully, this would be your final answer, right? So far, product sum method looks pretty good. Now, on the next slide here, I'm going to show you examples where the product sum method doesn't actually work. So in this case over here, some quadratic equations do not have a factor pair that will add up to the middle term, so b in this case. And as a result, you were unable to use the product sum method. So let's look at the first example over here. Y is equal to x squared plus 2x plus 2. In this case over here, AC is equal to 2. What are two numbers multiplied together gives you 2, but also adds up to 2. In this case, there are no numbers at all. So in this case, that's what I mean by you can't actually use a product sum method to factorize this particular equation. Similarly, for the next example over here, there are no numbers that multiply together that gives you negative 3, but adds up to positive 8. As a result, we can't use the product sum method. As shown by these two examples over here, if you're not going to be able to factorize it using the product sum method, this means that we wouldn't be able to actually find our x-intercepts. So one of the ways that we can get around this is by using a different type of factorizing technique, and this technique is referred to as completing the square. So we use this particular technique when there are no factors that give you the middle value, so that's b in this case over here. However, this particular method is quite complex and very time consuming. And to show you what I mean by this, I'm going to show you all the steps involved to convert this particular, factorize this particular quadratic trinomial. So as you can see over here, it looks a bit whack, but it is very complex and there are a number of steps involved. The reason why many students often find this particular technique confusing is because that, as you can see, completing the square generally involves using surds, but it could also involve using fractions as well. And due to these different elements, it makes this particular technique very hard. So let me have a go at explaining what this technique is and how we actually do this. So completing the square. As I said, we use this when the practice method doesn't work at all. But when we do factorize it, as I said, this does allow us to find your x-intercepts. One of the great things about completing the square is that it allows you to actually convert from the standard form into the turning point form. So what do I mean by this? So in this case up here, if you got this as an example, if you are able to successfully complete the square, then you can convert it into the turning point or the vertex form. So you're probably thinking, how do we go from this all the way to this? As I've shown you before, there are a number of steps, and there are also key things that you need to know beforehand in order to do this successfully. This first includes being able to recognize and factorize perfect square trinomials. So in this case, what I mean by that is if you see something similar to this, you can be able to factorize it back into this form over here. Or another example would be from this back into this form. So that's a perfect square trinomial. Similarly, you also need to have an understanding of how do you actually factorize a difference of perfect square as well. So being able to go from this form over here to the factorized form, okay, the one that has the sets of brackets. So let me show you like about 4 examples or so of what I mean by this. In the example x squared plus 8x minus 3, we're going to need to follow these 3 steps over here in order to factorize it by completing the square. The first step says we need to add and subtract by the constant b over 2 whole squared. So in this case over here, this is expressed in the standard form, so ax squared plus bx plus c. So b in this case over here is going to be equal to 8. So you just you substitute that into this particular formula over here. That would be 8 on 2. And in this case over here, we can actually simplify this further. We know that 8 can be divided by 2. That gives you 4. So 4 squared is going to equal to 16, okay? So once I've found what that is, I'm going to add and subtract 16 into this equation. And I'll show you what I mean by this. Now, I've deliberately color coded this in red because in this case, if you add and subtract by the same number, I'm not really changing the identity of the equation at all because 16 minus 16 cancels each other out. So I'm not really changing the actual equation at all. But by writing plus 16 and negative 16, something amazing actually happens. If I just underlined these 3 terms over here, you probably can see that this is an example of a perfect square, okay? So in this case, because it's a perfect square, I'm hoping that you can realize that you can factorize these 3 terms as x plus 4 whole squared. And I've rewritten as this on its own, so therefore that'll be negative 16 take away 3. And now I can simplify this part over here, the things that are outside of the bracket. So negative 16 take away 3, that's going to give me negative 19. So that's the end of step number 2. Now step number 3 wants you to factorize using dots. Can you guys see that this over here is one example of a perfect square? This over here, although it doesn't look like it, can be rewritten as a perfect square if we actually use surds. So therefore, I just want to jog up your memory that this is what a DOPS looks like. So we're trying to put it into this particular format over here. In this case over here, we're going to need to find out what the values of a and b are so we can substitute it into our DOPS formula. In this case, a is going to equal to x plus 4, b is going to be the square root of 19, and all we do is substitute these values into this particular formula. So therefore, this would be your answer, okay? Now, obviously, going through one example, you're not going to become experts, so I'm going to go through another example, okay? So in this case over here again, we're just going to use the formula b on 2 whole squared. So 6 divided by 2 gives you 3. 3 squared gives you 9. And what I'll do is I'll add 9 and I'll subtract 9, okay? And in doing so, the reason why I do this is because that this allows you to therefore recognize a perfect square and then factorize it. So in this case over here, if I just look at these 3 terms, the perfect square is going to be x plus 3 whole squared. And then I just rewrite the bottom parts as it is. And then I'll simplify it, okay? So negative 9 take away 1 gives you negative 10. And now that I've done step 2, this is now in the form of a DOP. So I'll now factorize the DOP. So A in this case is going to be equal to x plus 3. B is going to equal to root 10, and I'll just substitute it into my formula, and therefore this is going to be my final answer. And as you can see over here, once I've got this, I can easily use the null factor law if I wish to solve for the x-intercepts. So what I want you to do right now is I want you to please pause the video right now, give yourself 2 minutes, and then we'll compare our answers together. So the very first step is to get b, half it, and then square it, okay? So 12 on 2 is going to be 6. 6 squared is going to give you 36, okay? So what we'll do is we're going to add 36 and subtract 36 to our quadratic equation. So once I've done that, then this is what your equation would look like. And by examining the first 3 terms over here, this looks like a perfect square. So that's going to be x plus 6 whole squared. And then you write the remaining terms towards the end. Once we've done that, we're going to simplify this part over here. So negative 36 take away 8, that's going to give you negative 44. And once you've completed step 2, this now kind of resembles a dot. So therefore, I'm going to express this as a dot. So I need to find out the values of a and b. So we just square root both sides. Therefore, a is going to be x plus 6. And if you square root 44, because 4 can go into 44, 4 is a perfect square, so it's going to therefore be 2 on root 11, okay? And therefore substitute the values of a and b into the equation, and therefore this is going to be our answer. If you want to double check to see whether this is the correct factorized form, all you really need to do is expand this particular equation over here, and if it gets you this particular equation, then that means you've done this successfully. Let's now look at an example where we're going to be dealing with fractions, okay? So we're going to still apply the exact same steps. So what I want to do is I'll take the value of b, so 3 in this case, divide it by 2, and then I'll whole square. So 3 squared is equal to 9, 2 squared is equal to 4, so it's going to be 9 on 4. I'll therefore add and subtract by 9 on 4. And now what I'll do is I'll need to actually factorize this. Now, as you can see over here, because I've got this term over here as a fraction, it may appear difficult for you to actually factorize and identify what is the nice perfect square. In this case over here, for now, can I get you to please accept the fact that when you do get a nice perfect square, this number over here, when you do a perfect square, will always equal to b over 2, okay? So in this case, b on 2 is equal to 3 on 2. So therefore, that will always be inside of here when you do the perfect square. So in this case over here, my equation is going to be this, x plus 3 on 2 whole squared minus 9 on 4 plus 1 on 2, okay? So once I've done that, again, all you need to do is just simplify this. So therefore, make sure that the denominators are the same. So make sure the denominators are 4, and then I'll add them in this case. That's going to give you equal to negative 7 on 4. Now that's written in this form over here, I can rewrite this as a dot. So find the values of a and b respectively. A is going to equal to x plus 3 on 2, and b is going to be root 7 on 2, okay? And once I've done that, I'll substitute these values into my formula, and therefore this will be my answer. I did say that I did want you to accept the fact that whatever the numbers are inside the bracket, that's going to be equal to this term over here when you do factorize it into the perfect square. And I'm going to show you again why this is the case by going back to some of the examples we've looked at. So in this case over here, you probably realize that these two examples of here, I've never said anything that you have to substitute that value in the bracket, but essentially that's what you've actually been doing, okay? So in this case, have you noticed that in this case, b on 2 is equal to 4, and you substituted that 4 value over here, okay? You probably haven't realized that, but you've done the exact same thing for the other example. B in this case is equal to 6. 6 on 2 is equal to 3, and you substituted that b on 2 value over here, okay? So over here, I'm saying in each example, simplifying b on 2 will give the term inside the bracket when you're actually trying to factorize it in the perfect square, okay? So please note this down, and this will always apply even with difficult examples that do involve having fractions as well. So what I want you to do now is I want you to have a go of doing this question. This question will have some fractions involved as well. So try your best, give yourself about 3 minutes, and then we'll compare our answers together. So our very first step is we're going to get our b value and divide it by 2. So therefore b is equal to 9. 9 divided by 2 whole squared. And if I square each of these, the numerator and denominator, that will give me 81 on 4. What I'll do then is I'm going to add and subtract by 81 on 4. And once I've done that, then I should be able to factorize this quite readily. As I said, to get x plus whatever that is inside the bracket, this term over here is always going to be equal to whatever that it is inside the bracket over here. So in this case, that's going to be 9 on 2. Oh, I made a typo over here. That should be equal to minus 4, sorry. And once I've done that, I'll simplify this by making sure the denominator is the same, so I can add or subtract the fractions together. So therefore, I made the denominators the same. This will give me 97 on 4. And now because this looks like a dot, I can therefore factorize it, find out the values of a and b. In this case, this is what you should get. And therefore substitute it into this particular formula over here. And therefore, this will be your answer. I'm going to show you 2 more examples, so please bear with me. So in this particular example over here, it's a bit different from all the examples that we've looked at because this is a non-monic trinomial, so the coefficient is not equal to 1. Now in this case over here, you're going to have to make one additional step when you have a non-monic, and you just need to divide every term in the equation or in the expression by that coefficient. So in this case, divided by a. In this case, that's 2. So therefore, that's going to be your new expression, okay? And I've deliberately used square brackets for a reason, and you'll see why later on. Now, what I'll do is I'll now get b and divide it by 2. Now, b in this case is not going to equal to 6. It's actually going to be this number over here. It's now going to be 3, okay? Because we factorized it. So now it's going to be 3 divided by 2. And if I whole square that, it's going to be 9 on 4. Once I've got that number, I'll now add and subtract by 9 on 4. So therefore, this is what my equation would now look like, okay? And in this case here, what I'll do is I'm going to factorize these 3 terms. As I said again, over and over again, if to factorize this, that's going to be this number over here that's inside the bracket. So it's going to be 2 brackets, and I use this case a rounded bracket, x plus 3 on 2 whole squared minus 9 on 4 plus 1. Once I've done that, I'm going to simplify this by adding these 2 numbers together. In this case here, that's what this will equal to. And now that I've rewritten it in this particular form here, this is like a dot now. So I find the values of a and b and put it into the formula. Therefore, this will be your final answer, okay? Have a go for this question over here, and then we'll compare our answers together. So what I'll do first is I'm going to divide everything by 2. And once I've done that, then you should find out what is b on 2 whole squared. I'll add and subtract by that number over there. And then I will find the perfect whole square, simplify, do the dots, and therefore this should be your answer. Now notice in this example over here, because when I square root, I've got a nice number, so that which gives me 1 and 4. Therefore, no surds at all, and therefore you could add these numbers quite readily. Now you're probably thinking, so couldn't I just use the grouping method? And yes, you can, but I'm just showing you, again, there's another way that you could actually do this, okay? Now, the last thing I want to end the video with is showing you an example where you can't actually use the completing the square method to factorize. So using this same example, I'll do what I've taught you, okay? Same thing applies. Now, in this case here, once you reach this step, notice that unlike all the other examples, this now has an addition sign. And because it has an addition sign, it's no longer a dot. Why is that the case? Remember that a dot has a subtraction sign. Remember, difference of perfect square means difference, subtraction between 2 perfect square numbers. So as shown in this example over here, this would therefore be the final step that you could actually go to. You can't actually factorize any further when you've got an example similar to this where there's an addition sign, okay? What I want you to do right now is I want you to please answer the following textbook questions, okay? So answer questions 2, 3, 4. I did include another question. I did include question 5 as well, because I think question 5 is really good since this one involves fractions. Do 6 and 7. This is pretty much the end of today's video. Hopefully you're able to meet the success criteria. I'll see you guys again in the next video. Bye.